Hello there, welcome back to another video. Now this is regarding your quiz. Again, so any questions that require working out, make sure that you have your full working out there and fix yourself in this particular case as well. Okay, now uh, multiple choice are worth 1 mark each. However, we need to understand the physics behind it. Now, we are doing radioactivity, so most of the questions here are, I would say, a little bit related to chemistry, but mainly would be physics. Now let's take Now, what does the scattering of alpha particles suggest? Okay, so now what does it suggest? So what does it prove to us? Now, there are tiny piece of an element, so this is incorrect. That is, it doesn't show that. They're mostly empty space with a very small dense positive center, which is correct. They are solid sphere, are positive, no. No, so therefore the answer by default is going to be this one. Remember, so this is the Rutherford scattering experiment. So the Rutherford scattering show that there's a tiny little dense nucleus at the center, so positive, and then everything else just empty space. Okay. Now number two, which statement is best? Which one is best? Now radiation are emitted from unstable atoms. Okay. Now atoms. Now remember atoms. So this here is the nucleus plus the electrons around them. Okay, now that is not the case. This is wrong. Now radiation emitted from unstable nuclei, that is correct. Radiation emitted from stable nuclei, that is incorrect, and also incorrect. So therefore the answer is B. So because the nuclei itself, so the nucleus itself is unstable. Now why does it have why does it become why is it unstable? Now one reason, it has too many protons and neutrons in it, so that's what, so it gets heavier, therefore it's more unstable. Now let's move to the next one. Now, which one described the Rutherford scattering best? Now remember, there are two things that he saw. Yeah, so one thing he saw was that the alpha particles, so these are alpha particles, is shooting it. Okay, alpha particles, let me draw them, alpha particles. They go to the gold leaf. Now most of them are passing through, so most of them pass through. Again, I'll write down here, so most pass through. Okay, again, now for those of you who got this wrong, make sure that you fix this up. Now most of them pass through. Now few are scattered. Okay, now which one's, now this one's showing that all of them is passing through. This one, so it can't be this one. Now B is showing you that none of them go through. That's wrong. Now this one, C is showing to you that all of them go through and they scatter. Wrong, so therefore it has to be D in this case, because D, few of them, very few in this case, scattered, and most of them pass through. This is this one here. Okay, now which one is a wave? Okay, now alpha particles, we know it's what? It's a helium nucleus. Okay, now beta particles, we know what? It's what? It's a fast moving electron. So fast moving electron. So therefore, the one that's left behind is gamma. So particles, so we have alpha, beta, and wave is just gamma in this case. Okay. Now we've already answered question 5. Question 5 is going to be what? It's going to be the nuclei of a helium. Only the nuclei, because remember alpha particles is what? Alpha particle is 4 and 2. Yeah, so 4 and 2. Remember 4 and 2. Only the nucleus. So therefore, if I have to draw it, so we got 2 proton and then 2 neutrons. Total 4. Yeah, so 2 proton and 4 is the whole thing. Okay. Now gamma rays can be otherwise be what? So gamma rays, they describe as what? They are fast moving electrons. No. So gamma is a wave, so they're not electrons, they're not proton, they are short wavelength radiation, so very short wavelength, like this radiation in this case. Okay, so they are light waves. Remember this electromagnetic spectrum, so EM waves. Yeah. Now which one can be deflected by a magnet? Okay, now okay, now what is magnetic? That is the question you want to ask you. Okay, now if you take magnets, you move it around a light bulb, so nothing happened to the light, so it can't be this one. Again, we're using logic here. Again, let's say if you don't know this, so you need to use logic. Okay, so have you used magnets and then try to move the light with it? Does it work? No, it doesn't work. Okay, now gamma rays is also uh, gamma rays is also part of the waves. X-rays is also part of the waves. So therefore, the one that's left is beta particles by default. Beta particles, they are what? They are electrons. Okay, because electrons are charged particles. Okay, so they are charged particles. Okay, because they are electrons. Again, so we use logic there. Okay. Now, beta particles can be otherwise described as what? They are fast-moving electrons. They're not proton. They're not proton. They're not slow. They are fast-moving electrons. Okay. Now, gamma rays again. So this is repeated. So this you should be able to get this mark again. So if you go back, okay. So question 6, this is 9 is repeated. So you should be able to get the mark there. Now, which object would significantly absorbed gamma rays? Okay, so which one would take significantly absorb gamma rays? Okay, so in this case, it's going to be what? It's going to be B. Okay, few centimeters of lead in this particular case. Okay, now which type is deflected by a magnet? We did this one already, so it's going to be B. Okay, again, so you can see they're giving us 3 easy marks there for us to take. If you use logic, you can take them, otherwise you'll be stuck. Okay, now let's take what we got. Okay, right. Now, alpha particles, so which one absorb alpha particles? Now, alpha particles get stopped by paper, so therefore A is going to be the case in this case. Okay, so which one? It gets stopped by paper, so alpha doesn't go at all. Okay, now 11. Which one easily stopped? Again, so we've done this one already. So alpha particles, the answer is what? So alpha particles can easily be stopped by what? Can easily be stopped by paper. It can be easily stopped by aluminum. So everything in this particular case. So 11 is going to be C in this case. Yeah. All right. Now the diagram here is showing us which one shows correctly. So here what we have paper first, and then aluminum. But this one, so this one, which object can easily stop it? All the object can easily stop it. Now 15, beta particles for 15. So here, beta stops by aluminium. This one is nice and easy. You can see how easy it is. Okay. Again, so which one can easily stop the beta particles? Beta particles. Now, beta particles can stop by aluminium and lead. So therefore, for 12 is going to be C. Number 2 and number 3 only. Now, which one shows correct? We penetrated by this one here. Now, look at these. Look at that. Now, I know it's very hard to see, but you can actually see how that. You see that the line is thicker here, and here is thinner. So what's happening? Showing you how it has reduced. So this one, few. Okay. Now same thing here. So this one go through and then few again. So look, thick and then a little bit few. So therefore, which one is showing for gamma rays? The gamma ray is going to be D in this case. Okay. Now remember, lead is going to absorb most of them. So therefore, if you want to stop all of them, then you need to have an extremely thick layer of lead for it to work. Otherwise, it's not going to work. Okay. So what happened is, okay, so most absorbed. So only a few you can see. You can see how the thickness of the line has decreased. Okay. Now this one is nice and easy. Okay. Now what we have is we have a source. Okay. Let me see if I can do it somewhere. Okay. Let's do it. Okay. Let's do it. Let's do it in the corner. Maybe have to zoom in. Okay. So what we have? So we have alpha, beta, and gamma. So we've got alpha, beta, and gamma. So we have a source, emitting source, blah blah. Okay, so we've got paper. Let me do it like this. We've got a source, and we have the paper, P for paper, and A for aluminium. Now what we have is we have 1000, we got 15, and 500. So I mean at total, how much we have? We have 2000, 3000. So 3000 are the total. Okay. Now paper is going to do what? Paper. So this will stop by paper. So these two here will go through. Okay. Now after the paper, how much are we going to read? So we're going to be reading 2000 here, because what? The paper is going to absorb the alpha particle, so the alpha particle is going to go. So we're only left with 2000. So therefore we know that we have two options, two options in this particular case. Okay, so aluminium, what's going to happen to aluminium? Aluminium is going to absorb what? It's going to absorb the beta particles. So beta particles are going to go. Okay, so wait, where is it? So that's wrong. Let me go back. Can I go back? I'm gonna go back. Okay, anyway, let me just delete this properly. Okay, so go 500 here, and total this. Okay, now beta particles can be 1500, so therefore we're left with 500 in this case. So therefore, if I zoom out, so therefore paper 200, 2000, and aluminium this one. So that's how much will be detected behind each of them. Okay, this is simple maths. Yes, this is okay. Simple maths. Okay, you have 3000 at the start. So paper stop 1000. How much left? 2000. Okay, now 2000 go through aluminium. Aluminium stop beta particles. Aluminium stopping 1500. How much? 500. Done. Maths, easy maths. Again, if you got this wrong, you need to fix. You need to tell your maths teacher. Okay. Now, which one is true about gamma rays? Gamma rays, which one is true? Are they ionizing? No. Okay, they have no charge. This one, they move at the speed of light, so therefore it's going to be C in this particular case. Again, they move at the speed of light because, again, they are EM waves. Yeah, so they are EM waves. They move fast at fast speed. Okay, so we call them gamma radiation as well. So gamma rays, gamma radiation, they're the same. They have no charge. Good. Which one is true about alpha particles? They are highly ionizing. Good. They are negatively charged. It is wrong. They almost go at the speed of light. It is wrong. So they are only A in this case, highly ionizing. Why are they highly ionizing? Because they are big. They have 2 proton and 2 neutrons. Okay, so and for neutrons, and they're big as well. They're positive. Now, which one is not a use for radioactivity? Now, radio treating cancer. This is a use. So this is a use in bracket. Now, detecting leaks. If you remember, we did this. So this is a use. Now, sterilizing prepackaged medical instrument. This is the use. Now, adding it to food. Okay. Now, this is contamination. So this is this is contamination. So you are adding it to the food. That's contamination. So therefore, this here is not the use. Okay. This is how you kill people if they don't fix themselves. Now, number 19. Which one is true about beta particles? Okay, now beta particles, they are identical to electrons, good, and they go very fast. So we know they go very fast. Now the question says they go almost, so that is very fast. Okay, they're not going at the speed of light, they go very fast. Therefore, it's going to be I and 3 in this case. Now, background radiation is detected, found to be this much, blah blah blah. What is the corrected one? Again, so this is going to be mass again. So what we have is we have let's say we have background, we got the source, so we detect 15, 550, okay, and then from the source we have 300. So how much? Sorry, from the background we have this much. Therefore, it's going to be this. Take away this. Got 2. So the answer is B. Again, so this is we'll use logic in this case, yeah, which is maths. Okay, if you got this wrong, you need to use you need to fix your maths. Now, okay, so this is injected inside the patient. Now, which one is more suitable? Okay, now what we want to do is we want this to be able to come out. So we want something with high penetrating power, high penetrative power. Okay, plus we want something with long. Okay, so not too long / not too short half-life. Okay, now alpha particle, this is a no-no. This is a no-no. Beta particle, this is also a no-no. Okay, because they are going to be stuck into your body. Okay, and they're going to cause damage to your cells. Now we have gamma, and we have 30 seconds. Now 30 seconds is too slow. By the time they take you to the scanner, it's already gone. So therefore, the only logical answer is going to be D. gamma rays. Now gamma rays, why? Because it's highly penetrative, so it can leave your body easily. And 30 minutes, it means it's gonna, by the time they take you to the scanner, and then you have plenty of time to get this done. Okay, now this one's basic math, so we've got 0, 1, so this is beta particles, so therefore this would be 14, this would be 7. Okay, so the answer in this case is going to be what? It's going to be B. Okay, you see how easy this is? Now again, another maths question there. So this is going to be 2, 3, 4. Okay, and this is going to be 90. So the answer again is going to be what? It's going to be a B in this particular case. Okay, now one instance, blah blah blah, emits alpha particles or beta particles, sometimes emission gamma. What changes to this if it's gamma? Now gamma, what happened? Gamma is what? Is 0, 0. So nothing happens, so no changes. Okay, this is just basic logic. Okay, no changes. Again, it's a basic maths again. Okay, maths. Okay, if you got this wrong, your maths is wrong. You need to ask your teacher to fix yourself, yeah? So this is what? 91. Okay, so what answer is this? So the answer is going to be C. Okay, now half-life, what does half-life mean? Half-life is the time taken for the activity to half, because yeah, how much stuff is it giving off? Okay, the activity, how active is it? How many counts is it giving off? Okay, now this is alpha particles. Now remember it's 4, 2, so therefore it's going to be what? On the top it's going to be 1, 18, and then 8, 4. So 4, 18 is going to be C. In this particular case, 26C. Okay. Now what we have okay, uncorrected count from the detector. Okay, is per 10 minutes. Okay, so we've got 10 minutes. We are getting 27 there. Okay. Now the background on average is 30 count per minute. So 30 counts per minute from the. Okay. So what we need to do is we want to know in 1 minute how many counts are we getting. So therefore, we're going to take this number there divided by 10. So this will give us. So this is per minute. So therefore, 250 per minute. Take away 30. How much is this? This is basic maths. Yeah. How much is this? Can someone tell me how much is this? It's 4. Okay. Again, maths, logic. If you got this wrong, you need to fix your maths. Okay. There's nothing physicsy in this. Okay. Let's move to the next one. Okay, now the half-life is this. What fraction is it after 10 minutes? Now let's start. At the start, we have 100% of the object. Okay, now half-life means how long will it take to half itself. So after you get to 50%, and it took how long? It took 10 minutes. Okay, right now after another half-life, this is going to drop down to what? 25%. So this will be what? 20 minutes. Okay, again, so just logic, yeah, logic. So half-life is you start with 100% and then half of it after first 10 minutes, so that's the half-life. After the first half-life, so number 1, after the first half-life it goes to 50%. After the second half-life, which is another 10 minutes here, okay, it goes to 25%. So therefore 20 minutes. So after 20 minutes it goes to what? To 25%. Now which of these is 25%? 25% is a quarter. Okay, again, this is just maths logic. Now we've done this before. Which one is the graph? Okay, so remember when we did the practical, now by default it's going to be this one straight away. Again, this is like a nice exponential curve, goes down in this particular case, yeah? Okay, move to the next one. Okay, now here we go. What's the half-life of this one? So again, we do the same thing. So we start with 640. Okay, now after the first half-life, so this is the first half-life. Okay, what happened? Okay, first half-life, we go to 3.2. Okay, after the second half-life, we drop down to 1.6. After the third half-life, we drop down to 80. Now it's taken us 3 half-lives. So 1, 2, 3 half-life. Now how long is 3 half-lives? Okay. Sorry, how long is 1 half-life? Now 3 half-life taken us how much? 24 minutes. Yeah. So 3 half-life, 24 minutes. So therefore 1 half-life is what? It's 24 over 3. Okay, it's 8. Therefore, it's 8 minutes. Again, if for those of you doing the maths, you know there's a direct way you can take this one straight away. Okay. Right. Alright, so here we go. We have another one again. So which one is more likely? Which one is more likely? Now, you need to read the question carefully here, yeah? Now, the count rate is plotted. Now, without the background, what happened? Now, being first subtracted. Now, the background is always there, okay? Now, so this here is, okay? So, without the background being first subtracted, okay? So, this is including the background. So, included, the background included, okay? Now, without the background, the object is going to go down and get close to 0, yeah? But with background, this is what's going to happen, because the object is going to decay, and then this here is what you're getting is just the background. Okay. Now again, how do? We use logic, because it can't be this one. Now this is 0, so it can't be this one. So you're left with either C or D. Now the question tells us is we have the background. The background is always there, so therefore it needs to stay at a certain amount. So therefore is this one. Okay, so wake up. Okay, so this one, so 33 is the same as above. Okay, now let's do this one. So we got 264. The half-life is this. What's the activity after the first 2 minutes? Now, after the first half-life, so 3 minutes, we drop down to what? 320. After the second half-life, number 2, so this is another 3 minutes. Okay, drop down to 160. Okay, so 1, 2. Okay, after another half-life, another 3 minutes to 80. Okay, after another half-life, the fourth half-life, 3 minutes, and then to 40. Okay, so therefore we've got 3 times 4. So this is what is the half-life? What is the activity after the time? So therefore it is 40 in this case. Okay, here we go, done. All right, you see how easy it is? Again, I'm not even using like crazy maths. Just half, 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 and count. Half, 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 and count. 3 plus 3 plus 3 plus 3, done. Nothing crazy going on. Logic, maths. Okay, all of you do maths here. Now another one. So falls from this to this. Okay, look, we have from 8,000 and a time of 30 minutes fall for this. Again, do the half-life. Half of this is what? 4,000. So this is the first half-life. Okay, we go drop down 2,000. Second half-life. Again, drop down 1,000. Third half-life. Again, drop down 500. 4 half-life. And 4 half-lives. So 4 H for half, L for life, equal to 32 minutes. So it took 32 minutes to go from there all the way down. So it tells us there. Therefore, 1 half-life is what? 32 divided by 4. Now you guys can do the maths. Okay, you've been doing maths. 8 minutes again. Okay, how easy is this? Right, now this one's gamma. Now gamma is what? Gamma is shortest wavelength, highest frequency. So it can't be this one, can't be this one, can't be this one. Here you go by default. Look, power 21. That's the highest. Let's go for it. Okay, logic. Okay. Okay, let's take a look. Now, the count rate is 190, and the background is 30. So therefore, I need to take away to find out how much is coming from the source. So 160 from the source, and the time is from 10:30 to 11:50. So therefore, this is 1 hour 20 minutes. So therefore, we got 60 minutes plus 20. So this is 80 minutes in this case. Okay, we've got 80 minutes. Now the question says it has fallen during the time. It's fallen to 40 per minute. It says 42 per minute. So let's take a look. Okay, so we got 160. The first half-life goes to 80. Another half-life goes to 40. Okay, so we got 1 and 2. So therefore, 2 half-life is taking us 80 minutes. Now, 1 half-life is what? 80 for 2, we get 40 minutes in this case. Okay, so therefore the answer for 37 is 40. Did I do this wrong? Let me just check. Alright, so it looks like I made a mistake in this one. Okay, let me delete this one. So what I've done, okay, so this is still 80 minutes. It's 80 minutes. Okay, so I had to read the question again properly this time. Okay, let's delete this one, delete this one, delete this one, delete this one, delete, 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 delete. There we go. Okay, so what they've done is they work out the background radiation, which is 30. Now the uncorrected one is the one that measured. Okay, so they measured the uncorrected one. So therefore, it is the uncorrected one that is going down. Okay, so the uncorrected one goes down to 95. Okay, goes down to 45, and fall into this. Let's fall into this. Okay, let's fall into this, and then this will give me 23 something. Okay, so we got 1, 2, 3. Okay, so it's falling to 40 per minute. 40 during those times they're gone to 40 per minute. All right, so 40 per minute. We have two liquids. We have liquid A and B mixed. Now A has an activity of this one, and B has an activity of this one here. Now let's take a look how we can do this. Let's zoom in. Okay, so let's go. Alright, so we got A. Now write down here A, and then we have B. Now A has an activity of this, so do 30. Okay, now after the first 5 minutes, okay, so of 5 minutes wise, this has an activity of 2000. Okay, and its half-life is 10 minutes. I mean, it takes 10 minutes for it to half. Alright, so let's take a look. Now, in the first half-life, so A is going to drop down to 16,000. 1600, sorry, it's going to drop down to 1000. Okay, now after 10 minutes, what's going to happen to the whole thing? Now, after 10 minutes, so this guy, after 5 minutes, is going to drop down to 8 in this case. So therefore, it took A 10 minutes, therefore 2 half-life, but this one only took 1 half-life, which is 10 minutes to get to this one here. So therefore, what is the total? The total is 1800. Therefore, the answer is going to be D in this case again. So we are using logic to make sense. Okay. Now, what happened to the overall mass of the fission after and before? Well, before and after, isn't it? Before and after. Okay. Now, before and after, what happened is, remember, we have a big unstable nucleus, and then it's split into two smaller nuclei, and they are smaller in this case, a little bit, and not much smaller, no, a little bit smaller, and they're still big, and we have 2 or 3 neutrons being released. Okay, now which one is about the rules? Which one is about the rules? Okay, so must not be pointing, must not be pointing at the body. That is indeed correct. Okay, the sources must be moved with forces. That is indeed correct. Now you see that I and 3 is not there, but your hand must be washed if you touched it by accident. Therefore, it has to be all B3. Now this one we need to use logic. Okay, now we need to do this one. But if you remember, your best friend Albert, okay, Einstein, okay, the equation E equal to mc squared. Okay, so what it does is showing you that energy is turned into mass, and mass is also turning into energy at the speed of light squared. Again, even if you don't know even if you don't know what is it, but if you use logic, okay, so many people know this famous equation, Albert Einstein. Okay, so if you walk around on the street, you tell them, hey, do you know Albert Einstein? They said, oh yeah, I've heard of him. Do you know the famous equation of Albert Einstein? They say, oh yeah, E equal to mc squared. So even people know it. Okay, now what is the best description of an atom? So we've done this one already. A tiny neutral, so it can be this one. A large one, it can be this one. A large one can be this one. So therefore it has to be C, a tiny positive nucleus surrounded by neutrons, electrons. Again, so this is something that you guys done. Now this is basic maths. So this plus this, okay, what this one should be? Okay, now this two give me what? This two give me so this to give me 3, 4, 2, and these two give me 6. So therefore, what should this one be? Okay, so 236 to 236 234. Okay, so therefore this one should be 1. So this one should be 1. So this one should be 2 in this case. Yes, so this number should be 2. So therefore it has to be 2 in this particular case. Okay, another one there, so 45. Another one, again same thing here. So this is 236. Okay, so we got 3 in this case. So this is 3. Therefore, this and this give me 98. So therefore, what number should this be? Okay, so therefore this one here should be 1, 3, 8. We got this one and this one. Therefore, what should the bottom one be? The bottom one be, so this bottom one here has to be what? 56. So the answer is going to be C in this particular case. Again, logic. Now, what's the purpose of the moderator? It moderates. What does it do? It slows down. It slows down fast moving electrons. Okay, so it slows down fast moving electrons. Move down. Okay, now large pieces are called what? So we're going to have the unstable nucleus split into 2 daughter nuclei, smaller daughter nuclei. Now these daughter nuclei, they are the products. Okay, so they are what's produced in this particular case. Okay, they what's produced in this particular case. Okay, right now many people will think it is called the fragments. Okay, yes and no, but I don't know why. But it's products because you're producing those in smaller elements in this case. Now, which one is correct about the control rods? Now, the control rods do what? They slow down fast moving electrons? No. So this is what slows down fast moving electrons? So this is the role of the moderator. Now, they're made of carbon. Okay, we'll see what happened. Okay, they're made of carbon. We don't know. They're made of carbon. We don't know. Okay, but we know that they shut down the reactor. They shut down. How did they shut down the reactor? Because they absorbed neutrons. Okay, which slows down, which means there's less reaction. So therefore, it's going to be what? It's going to be. I'm going to put C there. Okay. Good. Now, when a nucleus of the uranium fusion, blah blah blah, what it is produced? Now, which element is produced? Now, this question here, you don't know which element is produced, but so yes, you do know. Okay, so we have uranium. Okay, so you end up with small, a little bit small, yeah, small, but still large. Okay, but large. Okay, so it can't be helium because helium is very small. It can't be oxygen. Oxygen is very small. It can't be sodium. Sodium is very small. So therefore, the only option is B, which is krypton and barium. Now, also, how do we know this? If we go back to a previous question, okay, look at this question here. It gives us krypton and barium. Let's go back to another previous question, 44. We have krypton and barium. So even without knowing what the answer is actually, but by using logic, okay, using previous question to help us out, we know what it is. And logic tells us if it's small, and here we go. Now, isotope, okay, thermal radiation, which one is going to be? Again, so which one is it going to be? Okay, how do we know? Look at the previous question, 235. The answer is 235. Again, look at the previous question. Where is it? Look, 235 is there. Look at the previous question, 235. So we are using logic. Okay, now if you got these questions wrong, then you need to ask yourself, where did your logic go? Okay, did you throw it out the window? What did you do with it? You need to wake it up. Alright, now in a controlled chain reaction such as the core, many fusion occurs. Now on average, must cause each. Okay, so now remember, we have uranium. We have one neutron goes into the uranium, and this goes, it split into, let's say, krypton in this case, and then barium in this case. And then we have 1, 2, 3 neutrons being released, and this neutron will go to find another uranium. Okay, now on average, how many further must cause? So on average, the least amount, at least we want 1 to happen. Yeah, now here we're getting, how many we're getting? We're getting 3 neutrons, so therefore we can go and start 3, yeah, which is very good, but at least we want 1 to happen, yeah, for it to happen, yeah, so that's what we're doing. At least we get 1, but in reality we're getting more than 1, but 1 is enough. Now, what percentage of isotope blah blah occurs naturally and enriched uranium blah blah? Now, which one occur naturally? Here we go. That is the question. Naturally. Okay, naturally. Now, look at this one. Where is it? 45. What's happening? We are using a neutron. 44. What are we doing? We are using a neutron. Now, if you remember what you've written down, okay, there are two types. Okay. Alright, let me just delete this so I can have some space to write. Okay. Now remember there are two types, yeah? You have the natural type and you have the induced one. Okay? You have induced one. Now induced one is the one that will make it happen. So to make it happen, what do we need? We need a neutron. So we need to fire a neutron at it. Okay? But okay, for it to happen. Now naturally it means it's gonna happen by nature. Now what percentage occur in natural enriched uranium? Now naturally, so you can see that in two questions already, question 45. So uranium 235, we are making it happen. Question 44, we are making it happen. Okay, and where is it? There should be another question. Here we go. In question 52, we are also making it happen. We're making 235 happen in the reactor. Okay, so which one takes place naturally? Now, so this here is induced. We make it happen. So it doesn't happen naturally. So the percentage of it happening naturally is very, very low. So the only possible answer is going to be 0.7. Okay, and then this here looks like this is the one that happens naturally. So therefore, this is going to be A in this case. Okay. Again, so we're using logic there. Okay, because because here you can see that three questions we're making it happen. Okay, now if 235 were to happen naturally, then we can, you know, we don't need to make it happen, but in this case we make it happen. All right. Okay, so here we go. Now which part is used to reduce or increase this one? So this is the control rods. Remember the control rods, it absorbed excess neutrons. Okay, now uranium 238 is not useful for producing heat in the reactor. Here we go. Okay, now because this here is natural, so this is natural. Okay, and we don't use it. Okay, we don't use it because the question tells us it doesn't produce heat. Okay, now if it doesn't produce heat, it means that it cannot be made to fission. It cannot be used to fission. Okay, is that correct? Yeah, it cannot be used to fission. Because remember, when fission happens, so here what will happen is we get energy being released, yeah, loads of energy being released, heat being released, yeah. So now in this case it means that occurs naturally. So occurs naturally. So what percentages of uranium isotope blah blah? Okay, naturally. In this case, it just takes place naturally. Okay, that's fine. Okay. Now it does not produce heat. That's your hint. It does not produce heat. So what makes it not produce heat? Well, it's not made to it's not made to fission. It's not made to break down. Okay, that's the only logical explanation. Yeah, in a nuclear reactor, when each fission reactor at least one further fission, what is the name of that? This is a chain reaction. This one we know. This one again. This is logic. We've done this one already. The nucleus of an atom always consists of one. So what is in the nucleus? This is chemistry. Yeah, this is like I think year 7 chemistry or even like year 6. What you've learned in chemistry. What is inside the nucleus? Yeah, what is inside the nucleus? Can someone tell me? Well, everyone will be like, oh, it's proton and neutrons. Yeah. Okay. Now, how do we know this one? Now, this one. What is this? What is this? Now, go back to question 43. E equal to mc squared. So we take this. We'll bring it here. So we have E equal to mc squared. So m, what's the m? The m is this one. So the m is this one. What c squared? C squared is the speed of light squared. So therefore the answer is going to be what? B. Okay, the nucleus of an atom, blah blah blah, consists. Okay, come on, you know this one. Isotope. What's the isotope? Okay, same proton number. but different neutron number. Yeah, so if they have, so you must have 6. So therefore, what's going to be the other one? So this has 14. 14 take away 6, what's going to be? Yeah, 14 take away 6, what? What is this? What is this? Come on, tell me. 14 take away 6, what happened? So it's going to have this 14 take away 6, 8. So therefore, 8. So 6 neutrons, protons, sorry, 6 protons and neutrons. Good. Okay, we're going to deal with this one a bit. Now, which one is otherwise described as nucleus? So we know this one, nucleus of helium, nuclei. Okay, now this one is something that you need to know. So, okay, let's have a look. So power is equal to energy over time. Okay, now what are we looking here? We're looking for the number of that takes place every single second. So every single second, yeah. So how many takes place every single second? Okay, what? Okay, so every single second, which is per second, yeah. So per second. Now remember, this here is what? Joules per second already. So joules per second already. Okay, so joule per second already. Okay, and then what's this one? So this one's watts. This one's watts, yeah. Watts. Joule per seconds, watts. Okay, so which one would it be? Okay, so which one makes sense? Which one make logical sense? Okay, so which one, when you do it, it will give you per second. Okay, so which one will give you per second? All right. What am I doing? Okay, let's do this. Okay. Okay. Now let's rewrite the equation. So what do we need? We need every single second. We need per second. So what we need is we need. Okay. Now let's do this. So power divided by energy is equal to 1 over time. 1 over time is what? 1 over time is 1 over second, which is per second, which is per second, which is per second, which is every second, which is what we need. So therefore the answer is going to be 500 times 10 to the power 6. Why power 6? Because it's mega divided by the energy, which is 3 power 11. So therefore the answer is going to be C. Again, if you got this wrong, this is the logical explanation. Again, so even though we don't know, even though we have not learned this, so we're trying to use logic in this case to think, okay, what is happening in this case. Now let me just go again. So any question that you go wrong, fix it properly for working out for explanations. I'm just going to scroll back to check if there's any question I missed. Okay, so this is the question I left out. Alright, so what we have is we have 30 from the background. Now this is the source. Now the whole thing together is 190. Now after some time, so at 10:30 the measured all together is 190, and then the measured again at 11:50, and all together is 40. Okay, now how long is the half-life from the liquid itself? Now what happened is we want to know. So now this 40 is including the background. Now if we take away that, so take away 30, we're going to have 10. Okay, so then we go backwards. So oops, so 10. Right, so therefore how much was it at the start? Okay, so again, so it would be 160. Again, so take away 30. So therefore half of that, so that's the first half-life, 1, first half-life, 80, second half-life, 40, third half-life, 20, and then fourth half-life is 10. So therefore 4 half-life, we have, how long does it take? So from here to here, so this is 80 minutes. So therefore that's 80 minutes. So one half-life is 80 divided by 4, so that is 20 minutes. Okay, so the answer is 20 minutes in this case. Again, so where you have to show you're working out, show you're working out. Where you have to show logic, you show logic. When you need to have the annotation, you show your annotation. Okay, so once you're done, you can crack on.